As a result of the way the periodic table is organized, certain trends tend to pop up. We're going to focus on four main trends: the size, meaning the atomic radius; the electronegativity, meaning the desire for electrons; the ionization energy, meaning the energy it takes to remove an electron; as well as, well, I guess that's it. And this is Screencast 6.4. Alright, periodic trends. Here's the major part of the periodic table. I guess it looks like the F block is missing. And there's a couple of measured values. One, size, atomic radius. Take a good look at that and see if you can see some trends. And here's another one, which is the electronegativity, where higher numbers are up towards the corner there. Alright, so from that we can deduce a few things. Alright, number one, I suppose we should point out that for the periodic table, trends, one of the main trends is that the whole thing's set up so that columns have similar chemical behavior. Flammable metals, also very reactive metals. No reaction at all, inert, nasty, noxious gases. Elements of life tend to be in here. And things like that. So you can find trends for similar behavior as you go down any of the columns. Boron, aluminum, gallium, indium, tantalum, all similar properties, for example. Okay, as we go down towards this corner here for this radioactive element, francium, which really is an exception since it's so darn radioactive that not much is actually measured about it. Most of this data really came from cesium just above it. But in any event, they get bigger, so size increases towards francium. By this diagonal line, we mean that it gets bigger as you go from right to left and as you go down. If there were two elements, like comparing, this one cesium to this one, whatever that is, it would probably be close to a tie, and it's not something you should probably ask. But others, it's simply a matter of what's closer. Okay, so that's the biggest, francium. These ones are smaller. And that's true. Do notice that the noble gases are somewhat of an exception. That's kind of interesting, isn't it? Fluorine, smaller. Fine. Hydrogen's probably the smallest. So, like anything in chemistry, there's a few exceptions. As we go towards fluorine, they want electrons more and more. Look at how high it is for fluorine there. Desire for electrons. It must be the red one there. I believe they've omitted the noble gases, because after all, they don't want electrons at all. Fluorine wants one desperately. One more and it can become isoelectronic with neon. So, that's the big word there. Electronegativity, desire for electrons. And that increases towards fluorine. Highest is fluorine. Lowest would be towards francium. Is francium the lowest? It's certainly right down there. See that there? There's another term, ionization energy. Now, that means the energy to form an ion. An unfortunate choice of terms since there's two types of ions, right? You got cations and anions. They specifically the energy to remove an electron. So what ion are they talking about? A cation. I mean, after all, the periodic table, some like 3/4 of the elements are metals. They all lose electrons. So it's the energy to lose an electron. The highest would be the one that wants to gain an electron the most, right? I mean, imagine the energy to remove something when it really wants one more. So it is also fluorine. So ionization energy and electronegativity follow the same trend. Thank God. Such weird big terms. It's nice that they're both maxed out at fluorine. So there you go. And those are the three major terms we'll learn about the periodic table. And this ends Unit 6.4. And unless otherwise stated, this ends the periodic table unit.